So I was asked to talk about BMS representations, which is a bit strange because I'm not at all an expert in representation theory. And I'm also not a mathematician, so I'm not sure I'm the right person to really do that. But so I will, at least in the beginning, I will talk about things that I know by reading about them, but that I don't know by having done all the computation. So I will just give you an overview of what I know in this setting. And then I will just cheat a bit and go to the things I like and present them like it was group theory, so that it fits into the theme. Okay, so I will make some standard remarks about the group, the algebra, the adjoint and the co-adjoint representation. Then the qualitative part of the talk will be about what I know, or what I will try to review with you the literature on unitary reducible representations of the BMS4 group, if you want. And then I will go over to something that I like more because it's more the classical theory and it's not about the quantum theory, which is talking more about just the co-adjoint representation and the orbit method, and not really trying to have immediately unitary representations. Of course, one of my favorite objects in this thing is these geometric actions that are due to Fadeev, Shatashvili and Alexeyev, in fact, and then I will make the standard remarks that you have heard me make before about BMS4. And if you stay to the very end, I will just make one slide about what I really wanted to talk about, but that's for the very end. So in the mid-60s, people realized that it was maybe unavoidable that if you are in the presence of, let's say, asymptotically flat gravity, that then in a very well-defined sense, the Poincaré group becomes replaced by the BMS4 group. And since at that time people really knew that in elementary particle physics, particles should be classified by unitary reducible representations of the Poincaré group, they were proposing that elementary particles should now be classified by unitary reducible representations of the BMS4 group. And so there was a paper by Newman, a Nature paper, probably one of the few in this field which was in Nature, and then also one by Koma, where they are really making this point. So they are saying, let's study unitary reducible representations of the BMS4 group, and then nobody did until the 70s, until McCarthy started to try to do that in a systematic way. Okay, because I will need it for the discussion that follows, let me just make some usual remarks. So if you study Lie groups, of course, lots of the information is already in the Lie algebra. And the simplest representation that you can think of is the adjoint representation, which in elementary terms is just you take the matrix representation furnished by the structure constants themselves, and because of the Jacobi identity for the structure constants, this forms a representation, of course, of the Lie algebra. That's the adjoint representation, and in these elementary terms, of course, the co-adjoint representation for finite dimensional Lie algebras is just to take the transpose minus the transpose of these matrices, which is the co-adjoint representation. So if somebody gives you a Lie group, these representations immediately exists, and on the level of the group, of course, the adjoint representation is really acting with the adjoint on the Lie algebra, and you get again an element of the Lie algebra. And the co-adjoint, if you have matrices, is also. Then the groups in physics, some groups in physics, if you're doing mostly flat space physics and not ADS or something like that, the groups almost very often in flat space have this structure, so they are semi-direct product. And I'm thinking the most important one, of course, is the Euclidean group of translation and rotations, in fact, which is very often used as an illustration of the structure of the BMS group, of course. The Poincaré group, translations and rotations, including hyperbolic rotations, the plane, and then BMS3, BMS4, and almost all avatars of these have this semi-direct product structure where usually you have very often a semi-simple group G, and you have a semi-direct product with an abelian group. And so in order to make on this a group law, what you have to do is, so you have two factors. The semi-direct factor is just the group law of the non-abelian group, which I refer to as rotations in general, just using the terminology from the Euclidean group. And then you have this action of the rotations on the translations, which is here. And the group law in the semi-direct product group is that you use the group law for the abelian part here. And you have to do something like that. And then it's, of course, an exercise just to work through the definitions of adjoint representation, of the Lie algebra, etc. When you do that, of course, you find that the Lie algebra is determined by the brackets in the non-abelian factor, but now you have the differential of this action on the infinitesimal translations, and you have to antisymmetrize that. So that's the first exercise to do. You have to do the exercise what the adjoint representation becomes. So you have the adjoint representation of the non-abelian part. Already this looks a bit more involved. You have the again the action of the group on the algebra, but you have to subtract something here. And of course, as we discussed before, the adjoint action of the Lie algebra on itself is just really the same thing then. Okay, that's one part of the exercise that you have to do. And then, because for all these group theoretical things, you always need the dual space, because you, as we will see, it's an important part of the construction. So if you need the dual space, you have to have a dual element to the non-abelian generators, which in general I will call angular momentum, I would say. So, and you have to have a dual space for the translations, which in this case, taking the notation from the Euclidean group, is linear momentum. And if you, for instance, do the usual BMS group, the only thing that you have to do is to add super to this part of the group. So you add super linear momentum because you have super translations. So you need the duals to the super translations. And here, if you want, you can stay with SL2C, with the Lorentz group if you want. But if you want to do any kind of super rotations, you also have super angular momentum or super associated to the super rotations. So, and then, of course, you know that in the adjoint, things go always the opposite way than they go in the direct construction. So the mathematicians in the 70s, well, I don't know which year it really was, but the ones who really studying semi-direct product groups invented this notation, this cross-product notation, which tells you basically that if you, so that's really the slightly non-trivial part of the co-adjoint construction, and it tells you that if you take a translation and you act on linear momentum, you produce angular momentum, in fact. And it's really, the way to think about it is what happens with the orbital part of angular momentum, which is really x wedge p. So if you translate x, so you produce with that an element, angular momentum, if you want, an element of p star. And this is the definition, and this is what comes out if you really do the construction of the co-adjoint representation for this group. So that's the only non-trivial part of the construction. You also need the adjoint action of the non-abelian group on the dual of the translations, and this is defined as usual because you have this pairing. Bring it over, but then you do the exercise, and the co-adjoint representation has what you expect for the rotation part, this angular momentum, this part of angular momentum, if you want, which is this orbital part it has always, and then there's just so that's the structure of the co-adjoint representation on the level of the group, and it's a bit easier on the level, as usual, on the level of the Lie algebra, and that's the structure of the groups and the algebras, and that's what we are going to try to study for BMS4 at some stage. Any questions on that classical part, I would say? So there's always this thing that you never learn completely in as much detail as you should, but that people, I mean, the generations before us really knew by heart, which is this Wigner-Mackay theory of induced representations for semi-direct product groups. So kind of usually what we learn is the summary that is given in the Weinberg book on how he classifies particles, but of course the full theory is much harder to do. I mean, really proving that you can get all unitary reducible representations of the Poincaré group by studying these little groups and doing induced representations for the little groups. The hard part is really to show that these are all the representations, that you can construct all representations in that way. That you get some representations in that way is kind of clear just on the formulas, but that you get all of them is the hard part, which I also only superficially studied. At least I know where to find it, and I will just show you where to find the full theory. So what you need in these induced representations, you need the duals of the translations, if you want, and you look at the unitary reducible representations of the abelian part, and because this is abelian, there is an argument which tells you that all of them have to be in this very simple form and involve just a phase times the momentum times alpha. So this is the classification of the unitary irreducible representations of the abelian part. So you get this exponential I pi p alpha. Yes. Well, I will talk a little bit about that, but I'm in this case, you can prove you get all of them. In the other case, the orbit method and things like that is an attempt to try to get all representations also from a similar construction, but it works less well. And I would say that's probably the object of the orbit method by Kirillov, trying to get for all Lie groups all representation in such a way. But it works because you see here you are not using the full co-adjoint representation, you are only using the action of the non-abelian part on this abelian ideal, and you induce from there, and the strong part is that you get all of them like that in this group. And in fact, well, let me not anticipate the idea. So the orbits that you are looking at is you look at the action of the rotations on this dual of the translations, which is really, and you are trying to see which of these momenta are related to each other by an action of the group. This defines you an orbit in the space of momenta, in the space of the dual of this A star, and at the same time, so the orbit is the set of all these p's related to a given p by an action of the group, and the little group is the set of elements of or the subgroup of elements of the non-abelian part that leaves one of these vectors invariant. Leaves this one vector of the orbit invariant, and then you can show just in finite dimensional Lie groups at least that this orbit is then isomorphic to the quotient of G of the group by the little group. And then what you're doing is you are defining equivalence classes of of momenta, and the two momenta are equivalent if they belong to the same orbit. And then what you do is you consider, so this is a linear space, so it can be R3, and you could consider the foliation of this linear space by disjoint unions of orbits. As usual with equivalence classes, you get this disjoint union. And so instead of, say, R3, you foliate R3 by spheres, for instance. So that's what you have to do. And then you choose a representative for each of these orbits. That's what you are instructed to do. Yes. Exactly, because of course, because the Casimirs characterize orbits, and so, but then having Casimirs is not enough in some sense, because you have to have enough Casimirs if you want to have a complete classification into orbits. I think people know. I personally, I have to say, you should look in the papers that I show you now. I'm not sure if he's phrasing it exactly in terms of Casimirs, because Casimirs is one way to give orbit invariance, but it's not maybe the only way. So it's not clear, but I think Laurent, they tried something with Casimirs on diff S2. Do it in that way. Of course, the Casimirs of the Poincaré group are very well known. There is P squared is equal to M squared, and then there's the squared of the Pauli-Lubansky vector. And in that case, they characterize already a lot of the things. Okay, and then you continue the procedure, and at the end of the procedure, somebody is telling you what you should do is to classify the unitary reducible representations of, for each orbit representative, you classify the unitary reducible representations of this orbit representative. For instance, for the massive orbits, you do a classification of the unitary reducible representation of SO3, because it's the rotations which leave this. Then there's the massless orbits, etc. But so you have to do all these. Then you have to understand how to induce a representation from here and from these characters that we had before, a representation of the full group. And so that's the next step, how to induce this representation. And under suitable assumptions, and they are satisfied for the Poincaré group, you can show, and that's really the hard part, there's imprimitivity systems and this exhaustive theorem. Under suitable assumptions, you can prove that all unitary irreducible representations, for instance, of the Poincaré group, can be obtained in this way, and that you haven't missed any. And this is specific to, let's say, the groups with this structure. It really builds, of course, on this work by Wigner, but then there has been these extensions by Bachmann and Mackay to make it more general. And then people have tried, of course, to apply it to the BMS 3, well, probably to the BMS 4 group, and the assumptions are not satisfied because basically one of the assumptions is saying that A need to be finite dimensional in order to do it in a simple way. And of course, for BMS4, this A is infinite dimensional. And then it becomes important in these infinite dimensional spaces, it becomes important what functional space you use for A, because if you make this finer, this becomes larger. And okay, this is the usual things about distributions, if you know. So there is, of course, one way to make this of the same size than that. I think in that case, it's the Hilbert topology, but I'm not an expert in that. But there's other choices. And the results that you are getting will depend on the choice that you make for the topology of, so how fine you make this and how large you make this. The results will not be independent of what you put on this infinite dimension. Yes, exactly. Indeed, in that case. But in the infinite dimensional case, this is more, then you have to define more clearly what you mean. And I think for the other ones, this is for the finite dimensional ones, anything is equivalent, everything is equivalent if you want. Well, I mean, you should look at what I meant by really going beyond Weinberg is you should take Barut and Raka or any of the, well, this is one where he does the full thing from beginning to end. He discusses this. But the assumptions that are fixed there from the very beginning exclude something like, but indeed, continuity and these things become important. And the beginning of this book is all about this continuity and what you mean. I don't know if somebody else has another favorite book to do induced representations of Poincaré, but it seems to me that this is one of the complete ones that the physicist can read. Okay. Yeah. I see. Okay. 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 If you can send me that references, I would be interested in, because you know every generation of physicists tries to find the best reference in that, and then you have all versions of watered down lecture notes of how it should really go. So for instance, more elementary is Cornwell or something like that, but it's, of course, he does the finite groups in some details, and then I think he does the hard stuff in a bit less detail. Okay, so if you do not know, so here is a kind of the review on that. So McCarthy really he was one of the first of the early authors of really studying that systematically. And for instance, what he was not doing, he was doing all the inducing representations and all the technique that is needed, but what he was not doing is really proving that you get all of them in that way. And this came a bit later by people from Dijon, associated to this group in Dijon, which completed kind of his proof by saying that this way for the BMS group still gives you all unitary reducible representation. So that was this paper here. The most important result that he got is the topology that he was choosing. Contrary to the Poincaré group, all his little groups were compact, and then he was claiming that the main result is that there are no continuous spin representations if you go from Poincaré to BMS. You should check. Okay, and then these people here, Girardello and already in 74, were pointing out that this result of not having continuous spin representation, which is really the physical result that they wanted, really depended on what you are putting as a topology on this thing, and that with other topologies, this result is no longer true. If you are interested in these questions, which are important questions, these are the references. So when we try to learn this, we were trying to apply it to BMS3, also a long time ago now, and it's in some sense simpler because the super translations is just a Fourier transform on the line, so you have it's a bit easier. But what is, of course, for BMS3 a bit more complicated is that also the non-abelian part is naturally diff S1, and so you have both becoming infinite dimension. We were also just trying to learn again how do induced representations go, what should you do, and how does this. Yes. Well, okay, have a look. I would say in some sense less because the continuous spin representations disappear, but I have a look at the papers. I don't want to make statements also. In a sense, but Okay, there is lecture notes by Jose on induced representations. Sorry, for Poincaré group, also maybe more from the homogeneous point. I think they are quite nice. I found them by Googling around what I should read. One of these versions. Okay, as I said, I'm not an expert. This is what I know from a distance. Now, a real expert can answer all your questions, but it's not what I had been really interested in. And well, it's what I always wanted to do seriously, but there's always these projects that you want to do and never get to finishing in all details. And, yes. Not really, because in the case of BMS3, you see it's all Virasoro, if you want, if you take central extensions, and there people have a very good knowledge of what topology they want to put or what are the rules of the game. But we didn't do any. We also mostly did just following what are the. So what we computed with Blaja is what. We followed this program, but we were not really proving that there were all of them and all of this. And then there was one guy who was a student, Melas, who was a student of McCarthy, who also studied this question for SO21 semi-direct product with the, so really putting himself again back in this thing, even though I think BMS3 is more naturally diff S1 semi-direct with the thing, because that's how it comes out, and there's absolutely, I mean, this is how it comes out without any singularity, as HDK and Bikac showed. BMS3 is very naturally diff S1 semi-direct. But of course, you can study SO21 and supertranslation in way, and then you are in exactly a lower dimensional setting, this one, where instead of functions on the square integrable functions on the sphere, you have really square integral functions on the, well, you have functions on the line.
You also need a measure.
Exactly. Yes, this is, yeah, Blaja had a lot of discussions with some mathematicians exactly on that, which is really, which is related to this part of the proof here, to this thing here. He was trying to get that maybe a bit harder, but you should talk to him if you want to know the final status. Okay, now to something I know a bit better and I like more, which is, so any more questions on unitary reducible representations of Poincaré? Okay, so in mathematics, there is this, what people call this orbit method, and it is an attempt to get all representations of a group G, and not only of the ones which have this semi-direct product structure, by quantizing some standard dynamical systems that have the group that you want to study, that you want to consider the representations of. You want to quantize this dynamical system, and this dynamical system is in a very specific way associated to a co-adjoint orbit. And the attempt by Kirillov is to say something very general on, for any group, on getting all its unitary reducible representations by studying this. And what you should read before plunging into that is, there is a review. So Kirillov has written lecture notes, which are lectures on the orbit method. And then in mathematics, there are people reviewing these lecture notes. And then there is a critical review of his program by Vaughan, who is a mathematician from MIT. And he's making an assessment of the whole program, why it should work, does it work, or etc. So this is the mathematics part of that. And it's very instructive to read because you know that there is this program, but he's telling you why, first of all, so you start by a problem in representation theory, you go over to a problem on manifolds and co-adjoint orbits, and the question is, what do you gain by this method in some sense? One is a problem in linear algebra, the other one is a problem in manifold, and it's never clear which one is more easy and which one is not. But the end message for a physicist is, this is exactly the kind of thing that you want to do, because you build up a standard system that has the symmetries that you want, and the idea is that if you quantize this system, you for free will get unitary irreducible representations of the symmetries. And I will try not to show you the mathematician's approach to that, but let's say a physics approach to that, and because this is what I studied and this is what I but for mathematicians, it's really, they try to use that to answer, in fact, your questions, to get all representations for any group, not only of this semi-direct product structure. And then, of course, there's a discussion that this, so Kirillov's method works very well for nilpotent groups. You get perfect results, but for the others, it's not, it's less. Okay? So let me give you the physicist's approach to this G-invariant dynamical system that you can associate to co-adjoint orbits, and that in principle you can quantize. And if you quantize it, you have built, in the Hilbert space of the quantum theory, you have a unitary reducible representations of the group that you are interested in. And of course, the main question is, again, like in the other case, why do you get all of them? Is it possible to get all of them? So what's the physicist approach to this thing? I think a very good way to think about it is in terms of effective actions, like again in Weinberg's quantum field theory book. So in a nutshell, what people are saying, so suppose that you have a group, a Lie group of symmetries that you know, but you have no idea what's the fundamental theory. You don't really know the fundamental theory that has this symmetry, and that you really can quantize the fundamental degrees of freedom. So Weinberg's problem then is, he wanted to construct a model that can be quantized and that has this group as global symmetry group by construction. That's what you want to do. Because if you have such a model, so by model, I always mean an action, because if you have an action, in principle, you can do, if you have an action, in principle, you can go to the Hamiltonian and you can do canonical quantization, or you can do path integral quantization. So by model, you should read action. It should have the symmetries, the global symmetries built in, and then you are trying to quantize this model. So the models that people were considering in particle physics were this kind of effective actions. And the point is that the models are built out of the data of the group itself. So you use as variables the group variables itself. So that's the idea. And if you are in the fortunate case that you have a killing metric on this semi-simple, let's say, Lie group, so that you are sure that you have a killing metric, then, for instance, the kind of pion effective actions that people have been considering are really this kind of effective action. So you really do dg g minus 1, you take as base space. So in this case, because they really wanted to do particle physics, you have also Poincaré invariance built in, because the indices are contracted, but Poincaré invariance is not the symmetry you are after. The symmetry you are after is SU3, for instance, or SU3 cross SU3. So you take SG, SU3 matrices, and then by construction, you have a theory that has SU3 as global symmetry group. And the fields that you are considering are really coordinates on SU3. That's the model that you would like to quantize in the case that when you have a killing metric. Of course, then you study the cohomology of that, you study effective field theories, and you put all terms compatible with the symmetries because you say renormalization is producing them, and then you get corrections to that, of course. But usually the kind of kinetic term that you put is this term to start. Of course, I mean, then you have to study invariance, etc. But this is kind of the starting point. Would you agree? Okay, but of course, one thing that you can do, and people have also done, even if you are interested in space-time groups, so there is a version of that where you take as base space, not space-time, and you have this Poincaré invariance, but you take just a particle living on the group. But then the more interesting question sometimes is to also take, let's say, Poincaré or conformal groups as this, to have it as global symmetry groups. Then you can already play with particle action like that. Of course, then the Poincaré invariance here is different than the Poincaré invariance. And I'm mostly interested because this geometric action that we want to do are related to this particle type of actions. So I will talk about these here and not talk about the fact where Poincaré invariance has to do with the base space, only with the target space. Very good. That's what precisely one of the things that I will discuss in a sense, but not for this model. This model clearly, because the killing metric is invertible, these ones do not have any gauge symmetry. The ones that the geometric actions that we talk about next, which is the ones of the Carrollian program, they usually have, of course, gauge symmetry. So, of course, this thing has built in this case, global right invariance. So sometimes it's easier to check. So you know that if you do Noether theorem and these studies, sometimes the symmetry of the action is easier to study in terms of the group. So for instance, if you want to check if something is Poincaré invariant on the level of the group, basically what you have to check is if your action is only built with Poincaré invariant tensors. Does it have eta mu nu, epsilon mu nu or not? But then, of course, if you want to build the energy momentum tensor or the Noether currents, you have to see how things transform under the Lie algebra. Also here, it is absolutely obvious to see why these actions are invariant under the group, and in this case, under right translation by group, by constant group elements, because we are talking about global symmetries. It's just because if you multiply this from the right by a constant matrix, it will cancel between, it will not be seen because it's constant by the derivative, and it will cancel between G and G minus 1. So this is just because these are the right invariant Maurer-Cartan form. So immediately when staring at the action, you know that it's invariant under the global symmetry. Okay, so this global right invariance is built in because this thing here drops out. Then, if you want to understand, if you want to compute the conserved charges and to do really compute with these models, and of course you can compute abstractly in terms of group elements, but this is not how we are used to doing field theory. We are used to doing field theory by telling precisely what are the fields, and then really working with these fields as coordinates. So in this case, you can do the exercise, but the good thing, and which took me a bit of time to understand this, so you can choose, suppose your group is SO3, you choose Euler angles, or you choose any parametrization that you want, exponential parametrization, so any coordinates on the group will go. So this is what I call GI, and think of them as Euler angles, but any parametrization is good. So that's coordinates on the group, and you fix yourself a basis of the Lie algebra. Then you take your favorite book on Lie groups and Lie algebras. In my case, I liked Choquet-Bruyas for that part. Okay, it depends what you like. And you translate all the abstract formulas that you have there in terms of coordinates, but in a sense, in terms of abstract coordinates because it doesn't matter which one you choose. If you do that, you do the standard exercise, you find that the generators of right translations are given by left invariant vector fields. So this is slightly, you have to go through the construction. The generators of left translations are given by right invariant vector fields, and you just do the construction. So in a sense, if you like GR, you should think of this as frames on the. So it's a bit like if you have frames, and if you compute the structure constant of these frames, what is particular about Lie group theory is that the structure functions of these frames are determined by the structure constant of the Lie group of the Lie algebra itself. Is like the D's are really the structure constants are really determined by this, and these two, for the left invariant vector fields you get the F's, for the right invariant vector fields you get the F's minus the F's, and these two sets of frames commute. And okay, so that's part of the exercise of understanding this kind of models. And then you have to express the left and the right invariant Maurer-Cartan forms because they are involved in the construction of the action. And you realize that the left and the right invariant Maurer-Cartan forms are just given in terms of the associated coframes. And of course, in this case, the torsion, if you do d theta of this thing, is again completely determined by the structure constants of the Lie algebra. This is what you usually have when you have frames and coframes, but it's particularly simple because they are globally defined, and everything is given in terms of this. And the other important, so you see that you have the inverse, so you only have two sets of matrices if you want the R and the L's and their inverse, and the adjoint representation in this language is just a combination of the left invariant frame and the right invariant coframe. So this is how the coadjoint representation goes. And then what the exercise tells you to do is you should write down this action in coordinates. And if you write down this action in coordinates, you see, since this is basically the right invariant Maurer-Cartan form, and here is the trace of the Lie algebra, what you are seeing is that this effective action in the case where the base space was a line is just given by the question that you should minimize this distance, and this Gij is just the dressing of the Killing metric or the extension of the Killing metric at the origin as a right invariant metric, so decorated by these matrices. So this tells you this is a very natural way to get the metric at the identity as a metric on the full Lie group. And once you have written the action, of course, you do not have to work anymore because then you know without doing the computation what the equations of motion of the effective action are, because the equations of motion for that, as you learn in either GR or a classical mechanics courses, the geodesic equation where the Christoffels are determined by this Gij. And then you can also check that in this language, of course, the right invariance becomes, as I told you, the generators for right invariance are the left invariant vector fields. And of course, then you check that these left invariant vector fields are really killing vectors of this metric, and you get the Noether currents in this language without having to compute. Is it clear? Okay, and so this geodesic flow equation on G in the literature is called the Euler-Arnold equation. It has been used. And then there is this Arnold theorem, which tells you that this geodesic flow equation on G has something to do with the coadjoint representation. So he's saying, there's a theorem, the second order equation for the G, the content of this is the same than a first order evolution equation for a vector which belongs to the dual of the Lie algebra. And then you try to understand this proof, but then you realize as a physicist that the proof is really basically just doing the Hamiltonian analysis of this. It's exactly the same thing. So suppose we do the Hamiltonian analysis of this action here. You would introduce, of course, conjugate momenta. So you would naturally do the Legendre transform, and you would do it if you want in Darboux coordinates. So you compute the piece. In this case, there is no gauge invariance. Who asked the question? There's no gauge invariance because this thing is invertible, and of course you can invert the momenta in terms of the velocities in terms of the momenta. But during the construction, you realize that maybe the good variables are not the momenta themselves, but the momenta which are dressed with this right invariant vector field. And so what this means is that it is sometimes, from a point of view of group theory, for once it's better not to work with Darboux coordinates, but it's better to work with this dressed momenta. So you have non-Darboux coordinates. Of course, the Poisson brackets of these momenta with themselves is what we already know from before. You just do the computation and you find from the properties of R that these Poisson brackets of this dressed momenta is just, they are determined in terms of the structure constants of the Lie algebra. And if you think about these pi's as coordinates on G star, this is the famous Kirillov-Constant-Souriau bracket that you get here just from the canonical analysis. So if you work in non-Darboux coordinates, this is the non-trivial part of the bracket. This is the non-trivial part of the brackets. The G's still commute, but the G's with the pi's are given by the, no longer by delta, but this R, of course, at the origin is also delta. And this is an element in G star. So if you now look at the Hamiltonian system that you have, as a first order system, you have in these non-Darboux coordinates, this is what you have. You have the evolution, the Hamiltonian evolution equations. This is the Kirillov equation. And then there's the other equation. But you know from your standard Hamiltonian analysis that the evolution equations for the coordinates is always just equivalent to the definition of the momentum. So this has no additional dynamical content. So this is the Hamiltonian version of that. And the Hamiltonian is basically, in this particular case, the Hamiltonian is the simplest Hamiltonian that you can put. It's built with, so it's quadratic in this momentum. That's why it's invertible, and it's built with the inverse of the Killing metric. And of course, the Noether charges in this case for the symmetry in the Hamiltonian setting are also very easy. Okay, I will not say more. Well, I will give, well, mainly because I learned it. So there are more general Hamiltonians, inertia operators. So all this has been important in the discussions of the Euler top and of this kind of problems. But of course, the really interesting part comes if you apply this to infinite dimensional Lie groups, because then you can see this flow equation. They really correspond to interesting equations in mathematical physics, like you recover the KdV equation when you take as the group the Virasoro group, and you have all this. So even for these groups, you get interesting equations if you extend the setting to infinite dimension. There's also something else which is interesting, because you have so many symmetries. You can prove that they are B-Hamiltonian and integrable systems, and there is a second compatible Poisson bracket that exists, which is not just take pi with pi, which is structure constants with pi, but put a fixed coadjoint vector here, and then you prove that this is a second compatible Poisson bracket that you can use to build your usual game. So I invite you to read the mathematics version, the more mathematical version of that, which is okay. well, let me skip this part because I'm already running low on time. Of course, also in particle physics, so this is also really, yes. Of course not. This will come. This will come. This will come in the next thing. In the next thing, as I told you, I will give you the classical. So I will give you the classical system that, and I will study the classical system that you have to quantize in the context of the Kirillov method, and that is going to give you unitary reducible representations if you quantize it. What I will do for you is do the classical analysis of this system and prepare it for quantization. That's what I will do. But here, I thought it was worthwhile to put it in a bit larger context because this is a nice chapter of mathematical physics that I was studying, so I wanted to show it to you. Okay, also, of course, these things are known basically in the supergravity literature because one of these sectors of supergravity uses this kind of action for the group, which is SL2R over SO2, because this is the axion dilaton system. And in this case, you also have an additional local gauge invariance, but let me not. So it is really an example of this with gauge invariance built in, which is really this kind of system. But the advantage is that by construction, so if you write the axion dilaton system, it's kind of very hard to see why it is SL2R invariant. Well, hard. It's not completely obvious to see that it has global SL2R invariance, but when you remember this construction as an effective field theory, it is obvious that it has to be SL2R. So now I will come to the classical system associated to the Kirillov program, I would say. So what would you do if you do not have a killing metric? Because lots of the groups that you are interested in, you would like to do the same strategy, but you don't have a killing metric to write down this system that you want to quantize. And what you always can do is you write, instead of doing these second order equations, you write just a first order Lagrangian, a first order action by using a fixed coadjoint vector. So you take a fixed coadjoint vector and you use still the right invariant Maurer-Cartan form. And by the same, so this again is built, now you have an external fixed vector, you have a group element, and by construction, again, this thing is first order, but it has the global symmetry that you want. You can do a bit more. You can add a class of Hamiltonians, which will always work, which is just to choose also a fixed Lie algebra element. And if you add this term, you can still check that this is invariant under right translation if you give the symmetry generator the right time dependence. So if the symmetry generator, the time dependence is determined by the bracket of x with y, if this equation holds, it's a one-line computation to check that this is still invariant under right translation. Exactly. So B is a fixed coadjoint vector that you put, this one is a Hamiltonian that you can put on your system and that you usually put, if you would do the path integral quantization of this model, it would give you the character associated to y. So that's the relation to group theory, because then you have like exponential of this trace of this Lie algebra element. And so that's why we are putting this kind of Hamiltonian. It's the easiest Hamiltonians that you can put that do not break this global symmetries that you want. But you can also just begin to study the kinetic term, which would be like Daniel was suggesting, and then afterwards try to see what other terms that you can add that do not break the symmetries that you are interested in. And this is one of these terms. There are others, but this is one class of terms. And then you want to do the analysis. So Kirillov's program would be use this as a model, and now our job is, this is the classical theory, it has the global symmetry built in, let's see what we have to do to quantize this system and to get the irreducible representation that we want. That's what I'm going to study, and I will just stop short of quantizing it. But I will try to set it up so that it's quantizable in this finite dimensional setting. Is it okay? Yes.
Beautiful things is created in Portugal.
Yes.
And the beautiful thing is, all these orbits are symmetric.
That's what I will show.
You are saying this now. Okay.
Yes, indeed.
Because that is, I mean,
exactly,
like
exactly.
No,
But well, of course. Of course, but the problem is that you have to deal with the natural gauge invariances that are there and that you have to quotient out. Okay, but indeed, but if you give as an example to a student quantize this system, okay, he will, so either he will try to do path integral quantization or will do Hamiltonian analysis and try to quantize. Let me do the Hamiltonian analysis of this. So you will see it's also a two-line computation to see that this system has gauge invariances, and the gauge invariances correspond to the little group or to the little algebra of this fixed vector that you are putting in the game. So you're putting this fixed external vector, and with that there is always the little group of that, and you just can check that these are gauge invariances of this particle model. Okay? And then you have to ask the question, as always, are these all the gauge transformations? Of course, it's not enough to see that you have gauge invariances, but you want to have all of them because you need to quotient by everything if you want to quantize. And so that's one question. There is another question that you can ask, which is, suppose you change this B and you use another B which lies in the same co-adjoint orbit. Do you have to study this model separately or not? Okay. Or suppose you change this Y by an adjoint representation. Is this a model that has different features, or is it enough to choose one model for each B which belongs to a co-adjoint orbit and each Y which belongs to, which is related to that by the adjoint representation? And the answer is you don't need to study this model differently, because you know that models are always defined up to field redefinitions. Field redefinitions that you can do give rise to equations which are equivalent in the quantum theory and in the classical theory. Right? You can do reparametrization in your Lagrangian formalism, and all solutions are, of course, the same. This is the covariance of the Lagrangian formalism. If you use this freedom to do field redefinitions, and in this case, the field redefinitions are very easy and just determined by the group. So you see that you only need to study one B per co-adjoint orbit and one Y per adjoint orbit. So these actions, taking that into account, have exactly the property that you want in group theory. Where did I put my pointer? Here. Okay, so in that sense, now you begin already to see that in order not to do an overstudy, you should classify the co-adjoint orbits and only study this model for each co-adjoint orbit. And for interesting groups, so the classifications of the co-adjoint orbits of a group, for instance, of the Virasoro group, is a famous problem, and it has been done by Russian mathematicians, of course by Kirillov. There's a very nice paper on, so how much of these models should you study? How many should you study? There's a famous paper by Witten and a very clear explanation also by some Hungarian mathematicians close to you, which gives you the different models that you should study. So here is in particular where co-adjoint orbits comes in. And of course, if you have this model, now I am trying to tell you exactly what is this dynamical system that you have to quantize and why it is a symplectic thing in the end. Okay? And it's of course only a symplectic thing after you have gotten rid of the gauge invariance. So the Kirillov-Coston bracket becomes only invertible and is the inverse to a symplectic thing only on the orbit, not on the thing. And of course, well, I'm already, I'm very slow. I'm sorry about that. So what you can do if you are a physicist to study the gauge invariance is to do the Dirac analysis of this model. And the Dirac analysis of this model has the good taste of being a purely algebraic problem. There's no, unlike electromagnetism, it's an example where you can do constraints, first-class constraint, second-class constraint, and you just have to do linear algebra. You don't have to do differential operators. And so if you do that, you find that first and second class constraints are completely determined by the null eigenvalues of this matrix, and that you can really solve this problem. And it has all to do with the null eigenvectors of this matrix. And then, of course, the inverse, the Dirac bracket, is an algebraic problem. It's not a differential problem. So that's a good thing. And then you know exactly what is your symplectic model that you use. So the reduced one, of course, you can do BRST, quantization, whatever you want, but you have complete control. So you can compute, it's one of the few examples where you really can compute Dirac brackets just by inverting matrices. It's a nice exercise to do it. And then you realize that most of these constraints are second-class constraints you can get rid of. But typically, the first-class constraints are, so the only ones are the generators associated to these little groups. And for instance, for the Virasoro group, they are very small. So the group is infinite dimensional. You have an infinite dimensional number of Gs, but in some sense, at most, 3 gauging variances. That's why in these character formulas, in the case where the little group is U1, you only use one of these modes. That I wanted to do. And more interesting to study is just to study a model where you drop all constraints, but then you're really talking about the model for T star of G, dropping all the constraints. So you can do, and that answers also your question. Dropping all the constraints means that you no longer say that this B is a fixed coadjoint vector, but it's another variable of the theory, but then you have double the variables. You have variables on the group, you have independent variables on the Lie algebra, on the dual of the Lie algebra, and you have the double number of conserved charges. And the equations of motions for the pi's in that case are very simple. They say that the pi's are constant. So what the mathematician would do is he would start from this model here and study Hamiltonian reduction on the level sets of this kind of surface. So that's another way to do the same physics. But I would say in the mathematics literature, people are usually doing this and Hamiltonian reduction, but you also can do the other way and Dirac analysis, and the end, of course. Okay, I'm running out of time. Of course, you can do that for ADS3, for BMS3, you get all these effective actions. I have already talked about that. A lot of time. So how much time do I have left? Okay, very good. Well, okay, let me not. Okay, but really, well, okay, but how much should I leave for discussions? Okay, but then let me just say some general things. So when we were studying this problem, it was, well, constructing everything is known about the BMS4 group. So constructing the coadjoint representation of BMS4 should just be a straightforward exercise. But as usual, sometimes these exercises are a bit of work. And in this case, it was a bit of work. And of course, what is very useful is to have the good language to phrase things in. And it turned out that the good language, the good language already was in the literature. If you want really to study what is the coadjoint representation of BMS, and you use this kind of understanding of the Lorentz group, how the Lorentz group is represented on the sphere, it is very useful to construct this coadjoint representation. So what you can work either in terms, so you have a two-dimensional conformally flat space. You can either work with conformal fields. So these are conformal tensor fields where you only do conformal transformations. And these P's here, which sit in the conformal factor, you can do complex Weil rescaling of these, where the real part you understand as a Weil transformation, and the imaginary part you can really understand as a local, as the remnant of the local Lorentz transformations when you just consider the Zweibeins. And then there's always two ways to talk about conformal fields. Either you talk about the conformal fields with this indices, or you can soldier all your indices into, if you want, the target space, and then, as in the Newman-Penrose, you're only talking about scalars. And but these scalars have some weights. So either you have this transformation laws under the conformal coordinate transformation, H and H bar, or you work with the weighted scalars, and then you have W and S, which are related to these complex Weil transformations, and these things then transform as scalars. So it's a two-dimensional version of what you are already used to when you study Newman-Penrose, and the interpolating map is of course using this ease to put all the tensor fields into scalars, and this is just certain weights in this conformally flat coordinates. It's just given by certain weights of P and P bar that of course then the covariant derivative on the sphere is really completely determined by this Weil factor. And if you want to preserve the full structure, what you really should introduce is a Weil covariant derivative. But it turns out that what we are interested in the end, for the construction of the BMS for group and its algebra, so there are certain weights in which the Weil connection completely drops out. And it turns out that in the case of the BMS group and the coadjoint representation of the BMS group, all weights and dimensions are such that you don't really need the Weil connection. Why this is so, I don't know, but you can read in Penrose and Rindler which are the weights for which you don't need the Weil, for which ETH and ETH bar, which are really the covariant derivatives on the sphere, for which combination of weights they preserve, they are conformally invariant. So they give you a classification of that, and all of these weights which appear here, which is what you need to build the coadjoint representation of BMS, are such that the covariant derivative you can just use at the end. You just can use the covariant derivative on the sphere. But then it turns out that in terms of these scalars, the super translation have spin weight 0 and boost weight 1, the rotations, so the generators of SL2C are represented like that. And then the interesting part is that this construction gives you the right weights for the super momentum, the super angular momentum, or just the J's and the thing like that. So as you know, the Lorentz transformation appear as things which, so the y's have to be close, ETH bar of y need to be 0. They satisfy an equation. So if the generators of the Lie algebra satisfy an equation, the dual is only defined up to equivalence classes usually. So that's the construction. So you know, of course, by heart almost the BMS4 algebra in these terms. And what is interesting, so you have in complete generality, you have a representation of the Lorentz group, let's say, on this spin and boost weighted scalars. And this is a bit like what you have in conformal field theory. So for each of this weight, you have a well-defined representation of the Lorentz group on these fields. And this is the way you talk about representation when you do field theory. But here it's really it's representations of the Lorentz group. Since it's representations of the Lorentz group, you should find them in the Gelf and Naimark discussion. Maybe I will make it. So this is a representation of the Lorentz algebra, if you want. And everything is determined by these weights, these two weights, which course, is also in symmetry. So, say it again. Okay, the weights are given here. So S is this, it's the spin weight, and W is the boost weight. It's the weight, if you want, under, well, it would be under conformal transformation. Well, they call it boost weight, but okay, it is, so in terms of the tensor fields, well, it depends which language you prefer. So one is H minus H bar, and the other one is H minus H plus H bar. It all depends on which language you prefer. Okay, and then you just do the exercise that you are supposed to do, and you build the adjoint and the co-adjoint representation. And the interesting part where people didn't agree, what was the right, so this is an important thing because it's super momentum, if you want, and the question is, what is the right weight for super momentum? And the right weight from group theory is 3/2, and there's no way. Romain is laughing, but I hope he's agreeing. But okay, and well, of course, you can do things a bit more explicitly, and then you can do the representations of the group. So in general, these representations, I mean, there is no guarantee they are irreducible. They are just representations. So here, this is the adjoint representation of the group in these terms, the co-adjoint representation of the group, and in terms of conformal fields, you get these formulas that you have seen maybe in different contexts, but what is fixed is all of these weights, just from group theory. If you now want, suppose that you really want to get the structure constants, that you really want to have the FABCs, what should you do in some sense? So you need a good basis, you need to expand everything. What does it mean expanding? It means putting everything in terms of spin-weighted spherical harmonics, and then you compute the structure constants. This is more difficult on the sphere than it is if you take the punctured sphere and the formulas for conformal field theory. So all I'm saying is this is a basis for expansion, and you can compute really the FABCs of the adjoint, of the co-adjoint, of everything. And it's, of course, a bit of work, but of course, some of it is just raising and lowering operators in a way. So you can get all FABCs, which is not yet classification. But this is really the basis, and that the spin-weighted spherical harmonics are important. You should realize, because when you look at the list of people who have studied them in one way or another, you realize that it is very important to have this basis. And for us, it was just important to get the FABCs. Well, okay, I wanted to say something about, so suppose now you try to do these orbits and you try to classify this. So you know that the super translations form a representation under the Lorentz transformation. So suppose you want to understand that representation a bit better. So the representation it's a representation of this type. As I was asked the question, so let me try to answer it. It's a representation of this type where the weights are 0 and 1. This should answer Ali's question for the super translations. That's what they are. Maybe you are more used to having -1/2, -1/2, because the -1/2, -1/2, you see them from the commutation relay. You see that the weight is really -1/2 here in terms of H and H bar weights. But so it forms such a representation of the Lorentz group, and you might be interested in how precisely, what are the irreducible components of that representation? Suppose you're asking this question. If you're asking the question, what are the irreducible? So the super translations are the spin-weighted spherical harmonics, which are here. So the spin weight S is equal to 0, if you want, W is equal to 1. And then you have a discussion of a kind of very short discussion of the Gelfand-Naimark representation theory in terms of spin-weighted spherical harmonics in Penrose and Rindler in terms of this diagram here. So what is he telling you? He is telling you that inside of this, so the the super translation you can expand like that. This is the dimensions of the spaces when you look at what happens with the rotation angular momentum. Okay, and so you see that inside the super translation there is a reduction to Poincaré, which is given by these equations here. So this is a finite dimensional, irreducible component of the super rotations under the of the super translations under Poincaré transformations. So that's one. And in this case, the representation is not completely reducible. It's what people call indecomposable. And it turns out that the other representation, the tail of the representation, which is the quotient of all super translations by the translations, that's also a representation of the Lorentz group. You can see that once you have a spin which is higher than 2, a spherical harmonic which is higher than 2, it mixes under Poincaré, under Lorentz transformation with everything. So it's not a decomposable representation. And the quotient super translation by translations turns out to be what people call the tail of the representation. And by chance, this turns out to be a unitary reducible. I don't know if this is useful in any way, but this belongs to the principal series. So this one is unitary. Super translations modulo translation is a unitary one of the Lorentz. Okay, that's one remark I wanted to make. I think I am done with this. Of course, there's the question where to identify all of this structure in the non-radiative data at Scry. That's an interesting question, but let me not talk about it here since I have been talking about that in other places. Before I do my final comments on some unrelated topic, are there some questions on this? Okay. So this one, if you do expansion, well, I'm not completely sure, but what I think is going on, if you do expansions in terms of spin-weighted spherical harmonics, you're using what people call, I think, the Hilbert space topology, where in some sense, the dual and the space itself have exactly the same size, because both of them you expand in term. It's like when you do Fourier series, if you want. And so the discussion I have made here is already the discussion where you say that everything is expandable in terms of spin-weighted spherical harmonics, and then so that's already a particular choice that you are making. So L2. No, this is really the sphere. I have not talked today. I have not talked about on the punctured sphere, which are super rotation. If you do that, all formulas are a bit easier, in fact, and are more conformal field theory like, because you don't need to make sure that things are globally well defined on the sphere. So you get formulas which are the same type of formulas, but you just do expansions in terms of Laurent series, because if you work with the punctured sphere, so you change, okay, if you mean the topology of the, okay, so there are two topologies. There is the, so this is really the topology with the puncture. So then you get conformal field theory type of formulas, if you really do that. Your basis of expansions is changing because you're different. You're doing a different, but basically you're doing S1 cross S1 and no longer S2. If you take the full sphere and you want things to be globally well defined, then you have this, and the expansions are the spin-weighted spherical harmonics. And the expansions are completely different. And the structure functions, the FABCs, are completely different. They are much more complicated because things need to be, so only the beginning looks like what you have on the punctured plane, but then you have corrections. This is completely done for the FABCs, I would say, but not for the classification. We have not done the hard part of the work, which would be to, which would really be to classify the coadjoint orbits and to do so this part of the work. So it's prepared for, but we have not done. But already setting up the right structure took us some time, how things depend on the topology, I mean, punctured plane or not. This, I think, we have now clarified in detail. Yes.
Then you could say, okay, I'm just interested in this.
Absolutely.
Something like this.
We have not done it in. We have not done it. We have done it in detail for BMS 3 with Blaja holographic positive energy theorems in 3 dimensions or something, which was really answering this question. Only the orbits, because there somebody else has done the hard work for us, because they know what are the good orbits for the Virasoro group. But in 4 dimensions we have not looked at. Oh, well, this model that we are going to give, strictly speaking, will only capture something about the non-radiative thing in the absence of nu, where you have conservation. It will not say something when you have fluxes. So then you need to correct this thing. Absolutely, absolutely. So, okay. Yes, but then you have to study the interactions of this purely group theory sector with, of course, the news and what is going. So you really can see, if you try to identify this structure in the asymptotically flat data, that you have to switch off the news in order to find the right combinations which have the right weight and which transform as they should. But for that, you need to switch off the news, because you know that here we will have conserved charges for this model. And that's interesting questions, but that's more questions about dynamics. But part of this work, of course, we did. I mean, you can look at, at least in the Newman-Penrose or in anything so in the Newman-Penrose, in non-radiative space-times, this is, of course, everybody knows that this is really the one which transforms with 3 halves, 3 halves. And this combination here is the one that transforms as angular momentum should transform, but there is corrections to it's not psi 0, and you don't need to put the electric condition. This is the one, and it's to realize that it transforms like the co-adjoint representation, you really have to work and understand these things about the sphere and really understand that there is a momentum map from non-radiative space-time to this thing without having to impose this electric condition. You don't have to impose that the shear is electric. So this is also... Okay, let me, in the last 5 minutes, let me try to talk about what I would have talked about here if I was free to choose my topic. So this is a kind of an obvious remark that goes out of this recent analysis so I realized that I didn't understand quantization, Hamiltonian formalism on null surfaces at all. I had no real idea how to do this, if Dirac analysis is going to work or not. And if you don't know how things go, you always should look at the simplest example. The simplest example is a boson in 2 dimensions, a massless boson in 2 dimensions. Okay? And you are trying to pretend that you don't know the system, and you're trying to quantize it on a null surface. And then you realize what the GR people know for a long time. It's not enough to have one null surface, because the characteristic initial value problem tells you that you need the complementary data on the other null surface. And in this case, the split is completely clear, because you realize that the left movers is the initial data that you give on one, and the right movers is the initial data that you give on the other intersecting null surface, and that it is that you only have the same information than the observer in instant form if you give data on both of these things. But I mean, in the initial value problem formulation, it's very well known, but what are the correct Poisson brackets and how you do quantization is a bit more tricky because you have to define Poisson brackets and things. So that's what we tried to study. But let me show you a very easy, I think, upshot of that. So when you study this, of course, you realize that the best thing to study the 1 + 1 dimensional boson is to do light cone coordinates, double null coordinates, x plus and x minus. And if you do x plus and x minus, the action becomes very simple. And if you do the Hamiltonian analysis, you realize that there are symmetries that I didn't know existed for the free boson. Of course, the free boson is a free theory. It has many symmetries that you can miss. But so the general solution is left movers and right movers. But you realize that the Lagrangian is invariant under this chiral shift symmetry. So not only, so the shift symmetries are well known, which is just that you transform phi by a constant because it only contains derivative. It's symmetry. But you also realize that if you translate phi by a constant that only depends either on x plus and on x minus, the Lagrangian is still invariant up to a total derivative. So these are symmetries of this system here. And in fact, they are more than symmetries. In fact, they generate the general solution starting from a constant one, if you want, because one is acting on the right movers, the other one is acting on the left movers, and with these symmetries, you can generate the solution. Maybe not so surprising. But then, suppose you would be a BMS aficionado and that you don't know that double null is the way to go in this case, and you would do the analysis in BMS coordinates of this system. So what would you see? BMS coordinates in this case is taking u is equal to x minus and r is equal to 1 over x1, if you want, right? That's BMS coordinates. Of course, now you are talking about a mixed initial value problem, and everything becomes a bit messed up, if you want. So the d plus and d minus one is still fairly simple, but the other one is a bit more complicated. So suppose you do a BMS analysis of this system and you try to construct a solution. So the way you would discover the solution would be that, of course, the left movers are what they were before, an arbitrary function of u. But the right movers you would discover as a tower of, so you would discover as subleading solutions, which are in this case just obtained by doing the Fourier expansion of this around r going to infinity. If you would do the BMS analysis, you would discover layer by layer in 1 over r, you would discover this part of the right movers. Okay? So that's one way to see things. But then it also turns out that this left chiral shift symmetry, which are kind of important, you would discover as a kind of infinite tower of subleading supershift symmetries. So you see that this is clearly not the right way of doing the problem. The right way of doing the problem, and so in this thesis by Smallwood, this is explained as an example. So in the thesis of Smallwood about the mixed characteristic initial value problem, and he's taking this same example to illustrate why it is better to do double null. Here you see that if you wouldn't do double null, you would really think that there is, so these symmetries look much more complicated than they actually are, because you are discovering them layer by layer, which is clearly not the way to go. So I let you draw the conclusions of this simple observation for the celestial or the Carrollian program, and I would think that one should really more seriously maybe try to go away from this if you want some things to appear transparent. Yeah, well, all is done here.
Yeah, but would you say
I think double null is the best way, but what we try to clarify is, in this case, is what are the rules of the Hamiltonian formalism on a double null thing? Because what is very strange if you do double null from a Hamiltonian point of view is that you see that this right chiral shift symmetry, which you know by all kinds of arguments that it is a global symmetry, it's generated by a first-class constraint. So you have to understand why first-class constraints can generate global symmetries. And this has to do with the fact, and Dirac already pointed out, with the fact that the initial data that you fix on one surface does not contain enough to completely determine the solution. So all goes back to this characteristic. So it is known, but then you have to work out the Poisson brackets. You have to understand how you get things. And we try to do a bit of that Hamiltonian analysis in double null. But so in U and R, you have a mixture of those. But even this analysis is better in double null. It's more symmetric in double null. You do it on one, you do it on the other, and then you combine the thing. In that case, that's what it is. Good question. Mass terms are more complicated in that case. Of course, all these things about these chiral shift symmetries go away in a sense. It is true, but of course you can see the massive one as a deformation of the massless one. And no, it's an interesting question. It's a good question. So there is this debate in light cone quantization that if you put periodic boundary conditions on the light, so that's what people call DLQC, putting periodic boundary conditions on a light direction. And you can prove that in that case, it's in the massive case, it's enough to give with periodic boundary conditions on the null direction, whatever that means, you can prove that it's enough to give data on one. But you still have the problem that in my opinion, it's still better to do it in a symmetric way, not to work in one, even in the massive case. So that's a debate in the literature on light cone quantization, but the massive is different. But precisely taking the massless one illustrates what you want to see. Here.